All right, this week we want to start out by talking about moment of inertia. So, I want to review the physics we've done sort of all semester. The three of the big ideas that we've had this semester. The first one was Newton's second law. And in Newton's second law, we said that force causes acceleration. And the way that worked was that F net was equal to mass times acceleration. Okay, and recently we've learned that torque causes angular acceleration, but we need something to put in here to be the rotational equivalent of mass, right? We've got mass up here in this equation. We need a rotational equivalent. So I just put it there as a black or a blue box. Similarly, we've talked about kinetic energy, 1/2 mass times velocity squared. So when we have a moving object, it has kinetic energy. Well, if we have a rotating object, it should also have kinetic energy. And again, the formula is going to be very, very similar. We're going to have 1/2. We're going to have something that represents a thing like mass, but for rotations. And then we're going to have the angular velocity, that is how fast it's rotating. So I hope you can see the similarities in these equations. For kinetic energy, it's 1/2 times the mass times how fast it's moving squared. And for rotational kinetic energy, it's going to be 1/2 times something that's like mass times omega squared. And then finally, momentum. Normal momentum is mass times velocity. And we're going to want to define an angular momentum, which again should be something like mass, but for rotations. So, what does mass tell us about an object? Obviously, it tells us how much material the object is made of, but none of these physics equations really deal with the amount of material an object is made of. What these physics equations deal with is a property of matter, really called inertia. That is, the more mass an object has, the harder it is to cause that mass to accelerate. So an object with twice as much mass needs twice as much force to experience the same acceleration. So the property we're talking about here for mass is this property of resistance to acceleration, or basically inertia. How much inertia does the object have? So what we need is a rotational equivalent of inertia. Okay, so let's think about if I had, let's say, a meter stick and a couple of masses attached to my meter stick, and I grabbed it at the center where that X is, and I started twisting it back and forth, right? I'm twisting it clockwise and then stopping it, and then twisting it counterclockwise and then stopping it, and then clockwise, counterclockwise, clockwise, counterclockwise. And I'll do this in class if we see each other in class soon. But you can sort of imagine that every time you try to speed it up, you try to speed up the rotation, that requires a torque from your hand. And every time you try to slow down the rotation, that requires a torque from your hand. And you twist it back and forth, you've got to apply torques left and clockwise and counterclockwise to get that thing moving and then stopped and then moving and then stopped. Okay, so here's the interesting thing. If we take those two extra masses and we move them to the outside, we have not changed the mass of this configuration. We still have the same ruler, we still have the same two extra masses. All we've done is changed the shape of the object. We've changed where those masses are located. But now, if I put my hand on the X and I start twisting this ruler back and forth, it is much more difficult to accelerate and then slow down and stop and then speed up in the other direction. It has a lot more rotational inertia. So what we now realize is that rotational inertia, and the scientific term for this is moment of inertia. Okay, so moment of inertia which I like to think of as rotational inertia. Or you could think of this as like rotational mass. I don't use the phrase rotational mass because mass has a very specific meaning, but rotational inertia gives you a good idea of what we're talking about. But the physics term that we usually use is moment of inertia, and the symbol for moment of inertia is a capital I. Now, moment of inertia is a complicated function of the mass of the object and the location of the masses, where all the pieces of mass are located. And in general, the further the masses are from the axis of rotation, the more moment of inertia an object has. So, the units of moment of inertia are kilogram meters squared, and the formula for moment of inertia depends on the shape of the object. So we've got several different shapes. Now, every different shape of object has a different moment of inertia based on the shape and size of the object. And what I've got here is just several examples. So this will get us through, I think, all of the homework, and you don't have to memorize these. A sheet like this will be available to you during the quizzes. So even if you've got a written quiz, you don't need to memorize these formulas. And so we've got some basic shapes here. So like a hula hoop, if it's rotating around an axis that goes through the center of the hula hoop, has a formula mr squared. A solid sphere has a formula of 2/5 mr squared. Not sure how easy that is to read. A spherical shell, that is a hollow ball, like a basketball or a soccer ball. A solid sphere would be a solid ball, like a lacrosse ball or a golf ball. So a spherical shell or a hollow ball is 2/5 mr squared. If we have a thin rod rotating around one edge of the rod, the formula is 1/3 mass times length squared. If we have a thin rod rotating around the center of the rod, it's 1/12 ml squared. And again, this is something we can test if we go to class, or you can test it at home. Grab any rod, like a length of pipe, or again, a meter stick, or anything that's got some weight to it that you can either grab at the center and try to rotate back and forth, or grab at one end and try to rotate back and forth. And again, what we're doing here is rotating it, not spinning it on its long axis, but rotating it around, rotating like a propeller. And you'll find that it's a lot easier to rotate around the center than it is to rotate around one edge. And that's shown here in the formula. The moment of inertia rotating around the center is 1/12 ml squared. Rotating around one edge is 1/3 ml squared. And we've got a couple of other important shapes. A pulley or a cylinder or a disc. Those have a moment of inertia of 1/2 mr squared. If we have a hollow cylinder like a wheel, that has its own formula for the moment of inertia. And then if we have a plate, like a square plate, again, rotating like a frisbee, that pulley is rotating like a frisbee. Also, it's 1/6 ml squared. So again, those formulas will be enough to get us through all the problems this week. But there are, of course, other shapes, and they would have their own formulas for moment of inertia. So you can see the moment of inertia depends on how much mass the object has, depends on the size of the object, and it also depends on the shape of the object. Okay, so those are all the basic simple shapes, but what happens if we have a complex shape like this meter stick? Well, if the meter stick's rotating around its center, then we would use the formula for a rod rotating around its center, which would be 1/12 the mass of the stick times the length of the stick squared. Okay, but what about these other little masses that we've added to the stick? Well, they increase the moment of inertia. So if this is mass 1 and this is mass 2, then we also need to know how far away those guys are from the axis of rotation. So I could call this R1, the distance from the axis of rotation to the first mass, and R2, the distance from the axis of rotation to the second mass. So the total moment of inertia would be the moment of inertia of the rod itself plus m1 r1 squared plus m2 r2 squared. These are called point masses or extra masses. So to find the total moment of inertia of a object, we can break it up into several different pieces. So another example would be if we had a wheel with a mass of the wheel and an inner radius and an outer radius, but we also had a rock that was stuck to the edge of the wheel, and we wanted to find the total moment of inertia. We'd say, okay, well, the moment of inertia is the moment of inertia of the wheel plus the moment of inertia of the rock. So we go back over here and we find, all right, what's the moment of inertia of a wheel? It's 1/2 m r max squared plus r min squared. Okay, so that's going to be 1/2 times the mass of the wheel times r1 squared plus r2 squared. So that's the moment of inertia for the wheel itself, and then I have to add the moment of inertia of the rock, and since that rock is just a small added piece of mass, what we need to do is just find its radius, which is also r2, and its mass, so this is just going to be mass of the rock times r2 squared. Okay? So we can calculate the moments of inertia of different shapes of objects, and that brings us back to our physics. And what I want to say is, in each case, the rotational version of the physics has moment of inertia in the formula. So when we're doing Newton's second law, instead of force equals mass times acceleration, we get torque equals moment of inertia times angular acceleration, or torque equals I alpha. For kinetic energy, instead of 1/2 mass times velocity squared, we get 1/2 times the moment of inertia times the angular velocity squared. And for momentum, instead of mass times velocity, we get moment of inertia times angular velocity. And so all of the physics we've already learned, we can basically, everywhere we used to have mass, we can put in moment of inertia. Everywhere we used to have velocity, we can put in angular velocity. And everywhere we used to have acceleration, we can put in angular acceleration. And we can learn the same physics for rotational motion.